Okay, so the topic of today is linguistic variables and hedges. So what does that mean? A linguistic variable is a kind of a variable that assumes linguistic values, also called linguistic terms. In order to illustrate that with an example, you see here on the slide the concept or the variable elevation, for example. So elevation is a linguistic variable, and that variable can have different values, linguistic values or linguistic terms. For example, low elevation, moderate elevation, and high elevation. So the variable is elevation, and the values, our possible values here, are low, moderate, and high. In the same way, when we think back to our previous example with the height of a person, you could say height is the variable, and the values are short, average, and tall. Or when we talk about slope, we could say slope is the variable, and we have two values, flat and steep, flat slope, steep slope. So that's the concept of a linguistic variable and their values. What you already see here is whenever we have a variable and we have values, and we want to represent those values with fuzzy sets, for every value of the variable, we need a separate fuzzy set. So in our example here, with elevation, we need one fuzzy set for low elevation, one fuzzy set for moderate elevation, and one fuzzy set for high elevation. And of course, for every one of these sets, we have to define a membership function. Now, this is the concept of variables and their values. Now, what is a hedge or a modifier? It's also sometimes called a modifier or a hedge. Is a hedge functions as a modifier of the meaning of a term. So it results in a composite term. Again, to illustrate it immediately with an example, when we have, for example, the variable slope and a value steep slope, so we can modify it, for example, with a term like very, making it very steep. So you can already see that there are a lot of these modifiers that we use normally in our, let's say, normal thinking or everyday language, like very, sort of, slightly. These are all such modifiers, and of course, we would like to represent these modifiers also in our fuzzy sets. So how can we do that? We use some certain operators that allow us to represent such modifiers. So these are operators that are operating on our fuzzy set. And on the next slide, you can see here some of these operators that are commonly used. There are four of them. They are called normalization, concentration, dilation, and contrast intensification. So what is normalization? Normalization means you divide every membership value by the height of the fuzzy set. You might recall that last time when we were talking about operators on fuzzy sets, we said there is one operator which is called the height of a fuzzy set. And the height is the greatest membership value in that fuzzy set. So whenever we divide every membership degree by the height, we definitely get one membership value, at least one membership value that is 1. So when you recall or look back to the slides, you will see I called a fuzzy set a normal fuzzy set when at least one membership value has the value 1. And of course, we can normalize every fuzzy set by dividing the membership values by the height of the fuzzy set. Assuming in the fuzzy set, the greatest membership value is 0.8. And so then 0.8 is the height, and 0.8 divided by 0.8, of course, is equal 1. So we reach a normalized fuzzy set by that normalization operator. Then the other one is called concentration. Concentration means we take the power of the membership values. The most common concentration operator is using the square of the membership functions. Why is it called concentration? If, for example, we look at, let me try to draw something here. If we would have a membership function that looks like this, for example, and we would apply a concentration operator, meaning, for example, we would take the square of all the membership values. Of course, since all the membership values are between 0 and 1, when we take the power of the membership value, the resulting number will be smaller, like 0.5 times 0.5 is 0.25. So that's why we end up then, for example, with a membership function that might look like this. And you see that's why it's called concentration operator, because the original membership function is somehow concentrated or condensed in a certain way. And the opposite of the concentration operator is the dilation operator. And one of the possibilities, or the most common dilation operator, is taking the square root of the membership values. So once again, if we would have a membership function looking somehow like this, sorry, that is a little bit tricky to draw with the mouse. And then we would use a dilation operator by, for example, taking the square root. Then we would end up with something like, so it's not exactly what I draw here, but I guess you can gather the meaning, what I want to say, so that it is somehow dilated or spread out. That is the purpose of the dilation operator. And the fourth operator is the so-called contrast intensification. The contrast intensification is defined in such a way that for every membership value between 0 and 0.5, we take 2 times the concentration operator. And for all other values, meaning for all values between 0.5 and 1, we take 1 minus 2 times the complement squared. You recall the complement of a fuzzy set is 1 minus the membership values. So 1 minus membership value squared is the square of the complement, or in other words, the concentration of the complement. So you could say it's 1 minus 2 times the concentration of the complement. Now, these are the major operators for fuzzy sets that we use to represent these modifiers or these hedges. Now, let's look at some common hedges, which are displayed on the next slide. So how can we represent things like you see in the left column, like a little, slightly, and just imagine, for example, the variable being temperature, and the value of our linguistic variable is, for example, hot. So hot temperature. And then we could say a little hot, slightly hot, very hot, extremely hot, very, very hot, more or less hot, or somewhat hot, indeed hot, or comfortably hot, or reasonably hot. Now, for all these expressions, we can use our operators that we just saw in on the previous slide. Now, for example, a little, we use a concentration operator with the power of 1.3. Slightly, we could use the power 1.7, and for very, we could use the square of the power of 2, and for extremely, we use the power of 3. And of course, very, very would be very squared, which is basically the same as the membership value to the power of 4. If we want to express something like more or less or somewhat, we use the square root, meaning we use the dilation operator. And then when we, for example, want to express indeed, so like indeed hot, we use the contrast intensification. And when we want to say comfortably hot or reasonably hot, in the example for hot as the value of our variable temperature, we would use the contrast intensification of the normalization of slightly and not very. So you might ask now, okay, why is that so, or what does it mean? I think the best way of illustrating that is when we look at a concrete example. And in fact, what I have here on the next slide is one example, like we had examples also in the last class. So we use a spreadsheet and we take the variable, the linguistic variable temperature, and the value hot. Of course, what could be values of our variable temperature? It could be hot or it could be cold, for example, cold temperature, hot temperature. We take the example hot temperature and we define our membership function in such a way that for every temperature below 20, it's definitely not hot, meaning the membership value is 0. And for every temperature above 35, the membership value is 1, meaning definitely hot. And for all other values between 20 and 35, we apply our a linear membership function, which is can easily be derived when you look at the definition of linear membership functions. And in particular, in this case, it's the increasing part, or let's say the left side of our linear membership function, which with the parameters 20 and 35, of course, results in our function x minus 20 divided by 35 minus 20, which is 15, as you can see here on that slide. And again, what we will do is we can represent that in a spreadsheet, and then we can try out our different modifiers. So again, what you see here in this slide would be the syntax for a function in Excel or in any other spreadsheet program. And we use the if statement. And if we have here the cells in A, in column A, we have the temperature in degrees, and in column B, we will have our result. So if we have a cell A2 and we want to compute the value in B2, we would say if A2 is less than 20, the result is 0. If A2 is less than or equal 35, the result is X, or in our case, our A2 minus 20 divided by 15. And in all other cases, it is 1, meaning all other cases will be those cases when the value is not less than 20 or less than equal 35. So meaning for every degree above 35, the result will be 1. In this particular example, when I say degrees and I define the function in such a way, it is pretty obvious that I will use a degree Celsius or degree centigrade and not any other unit of temperature. So let us now look at the implementation of that in a spreadsheet program. So I will jump to my spreadsheet. And here you can see in this spreadsheet, I have already prepared a table and a diagram where we will then graphically represent the membership functions for our particular classes that have been taken from the class hot temperature with certain modifiers. Now, again, let's see, we have here, I take degrees from 0 to 40, and then we would take the formula, which is already here. So I would just copy it. And by the way, you will receive that, or you will find that spreadsheet after the class on the website. So you can then try yourself or play around with it. So this is now the computed value. And now let's fill it down. And what you see here is that is the membership function of the value hot for the variable temperature. So this means hot. And if we look, for example, in, so if we have a temperature of, let's say, 30 degrees, the membership value is 0.67 to the class hot. And as we defined with 34 degrees, it is nearly 1, it's 0.93, and above 35 degrees, it's 1, so above 35. The membership to hot is definitely 1, so it's absolutely hot in our assumption, what we consider to be hot. Of course, as it all depends on the model or on the circumstances that you want to model. If you would model such a concept of hot in perhaps in Wuhan, then that would make sense, because in Wuhan you have in summer you have hot temperature reaching up to 40 degrees, and but when you would turn to Antarctica, for example, in Antarctica you will not have degrees, or you will seldom have degrees above 0, or maybe above 10. I understand there was some kind of heat wave last summer in Antarctica, but you would never reach temperatures, let's say, up to 25 or something degrees. So that would make no sense to have such a model for that region. But it, as I said, it always depends on your assumption of for which application or for which model you define your membership functions. Now, we have defined hot. Now let's look at a little hot. A little hot we defined as being the membership value to the power of 1.3. Now again, I could copy that here and enter it here in our spreadsheet. Oh, sorry, there is some mistake. So 1.3. Okay. So you see, you can in Excel you can express the the power using that character here. And if you are not familiar with it, I can tell you in Excel, you have all the functions that you usually need. You have financial functions, you have trigonometric functions, you have the whole mathematical toolbox that you can use. So we use it for our purpose here and express a little hot by using our example here. And as you can see, we have applied a kind of concentration operator. In fact, it's a very slight concentration operator using a power, a positive power of our membership values. And this is then the result. So when, for example, for 26 degrees, the membership degree to hot is 0.4, to a little hot, it will be only 0.3. So you see the membership to a little hot is less because the higher the temperature, the more concentrated the membership function will become. And then we want to model slightly hot. Slightly hot is what we said, we use the power of 1.7. So let me go back to our spreadsheet and enter the formula. Membership value to the power of 1.7. And then fill our table down. And we get now the result for slightly hot. Again, you can see it is more concentrated. And when we again look at our example, 25 degrees, or we had 26 and what I looked at before. So for 26 degrees, the membership value to hot would be 0.4, to a little hot, 0.3, and to slightly hot, 0.21. Now, in the same way, we want to express very hot. Very hot, as we said, we would use the square or the power of 2 for our membership values. So let's go back here and take the square of our membership value. And again, we have our result of very hot. So you see it's even more concentrated. So basically the slope of our membership function becomes steeper. So this would be the concept of very hot. So when we look at the example here, we had hot and very hot. Looks like this. So you can see this would be the concentration operator on our example. Okay, I will display the rest again. And now we look what is extremely hot. Extremely hot, we said, is to the power of 3. Again, we can do that. Membership value to the power of 3. And fill our values down. Which gives us, okay, I have to display it, of course. Which gives us this line here for extremely hot. And then finally, our very, very hot, as we said, very, very hot is 2 times very. If 1 times very is to the power of 2, then the second time would be to the power of 4. So we can do that. Very, very hot. We could say equal, I take very hot times very hot. That's the same result as the original value to the power of 4. And now we have our very, very hot. And again, if I apply a filter here to display our original hot, and then the extremely hot and the very hot, and perhaps also the very hot, the extremely hot, and the very, very hot, then we have these 4 membership functions that you can see here. And again, if we jump back to our table for 26 degrees, hot has a membership of 0.4. So 26 degrees are a member with 0.4 to the class hot, but only with 0.03 to the class very, very hot. So, and then we have another operator that we have here, that is the operator that we can use for more or less or somewhat. So if we say somewhat hot or more or less hot, we can use the dilation operator, which is equal to the square root of the membership value. So we can use the square root of our membership value, and then fill it down. Of course, I have to display it. So let's take the original and more or less. So what we see here is the linear function was our original membership function of hot, and somewhat hot or more or less hot is that function. And again, when we look at the degree of 26 degrees, has a membership degree of 0.4 to hot, but a membership degree of 0.63 to more or less hot or somewhat hot. Now, the next one is our indeed hot. When we look back to this table, we said indeed can be expressed with the contrast intensification of our membership value. And the contrast intensification is defined, as we can see here, for values between 0 and 0.5. It's 2 times the concentration operator, and for all other values, it's 1 minus 2 times the complement squared, or 2 times the concentration of the complement. So we can, of course, represent that also in an Excel expression. So if the membership value is less than or equal 0.5, it is 2 times the concentration operator, which is this here. So using 2 times the square. Otherwise, it is 1 minus 2 times the complement squared. So again, we can take this function, this Excel function, and apply it to our table here. Okay, something is wrong. What did I do wrong here? Okay, it's not B2. In my table, it's B3, of course. So I have to change it. My B3 is the cell where I have the membership value. So B3. Now it's okay. Now we fill it. And now we have our indeed hot. So what you can see here, and I will take the more or less away so that we can see that indeed hot now means for membership values below 0.5, it's a concentration, and for membership values above 0.5, it's a kind of dilation. So again, when we look at our value 26 degrees, we have 0.4 as a membership to the concept of hot, but only 0.32 to the concept of indeed hot. So again, you see it's pretty straightforward to do such computations. And now, finally, I want to represent the reasonably hot. The reasonably hot, which is defined as the contrast intensification of the normalization of slightly and not very. So what we first need is the normalization of slightly and not very. We have both here. We have slightly hot and not very hot. So slightly hot is here, and very hot is here, and the not is the complement. So slightly hot and not very hot would be our slightly hot. And now the end operator, you recall, the end corresponds to the intersection operator of two fuzzy sets. And we can represent that by using, for example, the minimum operator. That would be the simplest operator, but also it's a so-called non-interactive operator, if you look at the last class. And then there is one which is the multiplication operator, or the so-called soft intersection, meaning the multiplication of the membership values of the corresponding fuzzy sets. So what we will do here for the end, we will use the soft intersection and say it is our slightly hot multiplied with the complement of very hot, meaning not very hot. So the concept of not is expressed using the complement, and the complement is computed by 1 minus the membership value. So this would be our slightly hot and not very hot. And again, we can compute that value, values. And when you again look at our formula, so we have now slightly and not very. And now we need the normalization. The normalization means we have to divide all membership values of that fuzzy set by the height of the fuzzy set. So what is the height? The height is the maximum membership degree. So in fact, when what we have to do here is we need the maximum membership value of this set, slightly hot and not very hot. Of course, we can do it easily by applying the Excel function max, the maximum of that range, which gives us 0.28. So that's the maximum or the height of our fuzzy set. So you see the height here is, of course, not equal 1. It's 0.28. And the normalization is computed by dividing every membership value by the height of the set. Sorry. Okay, so this is now our result. That would be the normalized fuzzy set. And in fact, we can also display it. So we have hot, slightly hot, and not very, and then the normalization. So what you see here is this would be the result of our slightly hot and not very hot, with the highest membership value of 0.28. And this is then the normalized fuzzy set, where of course where we originally had 0.28, we have now the membership value of 1 because it's normalized. So we already are at this stage here that we have the normalization of slightly and not very. And now we need the contrast intensification of this result. And again, you recall the contrast intensification is defined like that. So for all values less than or equal 0.5, so this, if our value is less than or equal 0.5, then it's 2 times the concentration otherwise it's 1 minus 2 times the complement squared. There's somewhere a missing bracket, I guess. Let me see. Okay. Okay, that should be okay. And then see if, yes, so this is then our result. Again, let me verify. We have 2 times the concentration, otherwise 1 minus 2 times the complement squared. So 2 times concentration, otherwise 1 minus 2 times complement squared. Fine, so this is now our result for reasonably hot. And I will take now away the normalization and this one, and keep only hot and reasonably hot. So you see here in this diagram, only at a range between, let's say, what do we have here? 29 degrees and 31 degrees, we would have a membership value of 1 to reasonably hot. And for all lower temperatures or higher temperatures, the membership degrees decrease and are less. So this is a representation of the concept reasonably hot. Our results here. So these are the results that we have calculated, and that would conclude our example here. Exercise number 1, which you have to do now. It gives you a membership function for the fuzzy set far from something. Yeah? It is given in the way that if far from, meaning a distance from somewhere. So if the distance is less than 100, the membership value is 0. So that meaning definitely not far. And if the distance x is greater than 1000, let's consider it to be meters, for example, then the membership value is 1, meaning definitely far from. And in between 100 and 1000, the membership degree increases according to the formula x minus 100 divided by 900. So that's the membership function for the concept or the model or the class far from. And what you should do now is you should make a spreadsheet where you implement that membership function, and then you should create the fuzzy sets for not far from, not very far from, and very, very far from. And you should display that in your spreadsheet with a diagram in steps of 100 between 0 and 1200. So meaning in the end you should have a spreadsheet like we did in class. Okay, what you see here is the result of this first exercise. So once again, the problem was you should implement a membership function for the concept far from, which is given by that formula here. So to implement the formula, you just have to use the if statement in Excel, as we did in all our other exercises and examples, but you have to translate, of course, this formula into the proper Excel. So let me just make that a little bit bigger. So what you see here is the formula. I will do the following. I will copy it and so I copy the formula here. What you have to do is, again, use the same if statement. So if the value is less than 100, the result is 0. If the value is greater than 100 and less than 1000, then the value is cell value minus 100 divided by 900. And in all other cases, it is 1. And then I said you should do that for a distance between 0 and 1200 in steps of 100. So these are the steps of 100, 0, 100, 200, 300, 400, and so on until 1200. And here is the formula. So if for the distance of 200, the membership degree, according to our formula, is 0.11. For a distance of 600, it's 0.55, according to our formula. And from 1000 on, it's 1. And then you should do calculate not far from. So not is the complement. It's 1 minus far from. Then very far from, we said very is the concentration operator. So we use the square of our membership value. So very far means taking the membership value of far and use the square. Then not very far, it's the complement of very far, and very, very far, of course, is the membership value to the power of 4. So the most important task is to translate this formula into an if statement, as you can see here. To translate it into that statement. So what you have to learn, or what you have to practice, is how to translate such a formula into an expression in Excel using the if statement. So what you can do is, if you're not familiar with that, go to the help function and read the help about the if statement.